So we attempted a Monte Carlo algorithm, and we practically performed the calculations using the dice. So we draw the region like this, and there we have the red line, and we throw the dice, two dice together, and we said that the 6 is 0, so that we get the points between 0 to 10. So we generated x coordinate by throwing the dice, two dice, and we generated the y coordinate of the point by throwing the die. And with my students, I got the results. And let's summarize Monte Carlo in class. So in 50 trials, they got 36, 41, 47, and 39 hits. The points below the red line. And then we computed the mean number of hits and mean number and the standard deviation in the hits. So the value turned out to be 40.75 with 4 standard deviation. And we computed the area of that region. It was mean hits divided by n multiplied by the total area, which is equal to 1. So this was the one quadrant of circle. This was equivalent to one quadrant. So when we multiply it with 4, it became the area of circle. In the simulation, we got the answer up to 3.26. Now let's do that in a Python program. And the Python has a random number generator, which generates random numbers between 0 to 1. So if I write here, for example, numpy from random library, so when I write random, so it returns a random number, 0.9. If I again call this random number, so it's a different value. If I say random.random5, so it is going to give me an array of 5 random numbers. So this random number is the algorithm of Mersenne twister, right? So let's first write a part of the code. For example, I say for n equal to 100, I would like to plot the random numbers as well. So I import a library, import matplotlib.pyplot as plt, so that I can show. Now I define n points, for example, 1000. We can afford a larger experiment with computers. So I say, I first define a frame for my plots, x0, y0. I define plt plot xy, and with a very small dot. Then I generate x limits, and here I would like to show from 0 to 1, and similarly for y. My students had the graph paper already, so they don't need to create the frame. Okay, that's fine. Now I generate the random points. So for I in range n, so I define x equal to numpy random.random. The x coordinate that we generated in real experiment by throwing the dice, two dice. Now the second one, generate a point, and then everyone plotted that. Algorithm is consistent with the with the practical demonstration. That's it. So white space is important. This is end of for, right? So up to this point, I'm only interested to plot the graph. 1,000 points will be plotted, and let's see whether we appreciate oh, the plot is not there. X limit, Y limit. Oh, I have not provided any attribute. So blue circles. So we have got 1,000 points. So with these points, you cannot identify a pattern. That's why we say these are random, right? And they are uniform, right? We can later on increase this number, right? So now let's do the other check where these points have fallen, right? So let's assume, let's see whether they are inside a circle or not. And now I define my counter. Hitting inside the region, I define n hits equal to 0, right? Now the condition, I define a condition. I define a number, or for example, the radius. So I define numpy. This is drawing the curve line. SQRT of x squared plus y squared. So this is like the line. And now I say if r is less than or equal to 1. So it means it is inside the region, right? So I say inside the region or is under the curve. The point is under the curve. We are looking for area under the curve. So two gaps. In this case, I say n hits are equal to count one more hit, right? So I say plus equal 1. This is like the conventional command, uh, like n hits equals the old value of hits plus 1. So you can write the conventional way as well. Now I say if it is hit, then LT plot this one as red circle, right? And else plot this one as blue one. Make this distinction, right? So that we can see that one clearly. And this one is going to be the end of the loop. End of if structure, end of for structure. So I first plotted the points and then I make a demarcation that one are under the area, under the curve, the others are outside. After getting this one, now let's compute the probability. Probability would be equal to n hits divided by total n, and the area, the way we compute it, the area, the value of unit circle, it is the value of pi. I say it is v pi. V pi would be equal to probability times 1, which is the total area, and this is the one quadrant, this is the first quadrant. So for whole circle, it is 4 times of that. And this is the value we expect to be very close to pi. So now the print statement, the conventional value of pi, well, we should say Monte Carlo value of pi, right? Monte Carlo value of pi is equal to Monte Carlo value of pi, the variable name, and let's print with the pi of numpy. It is equal to numpy dot pi. So that's it. So the point is inside under the curve are the points red and the others are blue. Here we go. So we have got the bright right, where my mouse is, bright right, which says things are correct. And let's see. I am swinging on Professor Lewin's pendulum. 3.19, and pi of numpy is 3.14, and the figure is also there. And our algorithm was exactly the way you performed the experiment. Monte Carlo comes with the promise that if you increase the number of trials, say 5,000, it will cost you time and the number of calculations. But if you can afford them, I'm affording them because I'm using the Google's Python. So 3.14, accurate up to two digits of precision. Value Monte Carlo value of pi 3.1448, and real value 3.14159. And we have got the picture, right? So area under the curve is possible with Monte Carlo if you know how to write this algorithm and modify this algorithm.